Example 4C. Our system is 3x plus 7y minus z is equal to 11, x plus 2y minus z is equal to 3, and 2x plus 4y minus 2z is equal to 10. Okay, so we're going to start with our initial augmented matrix. Okay, so we are going to write it down. All right, look at our first equation. There is a 3 in front of x, 7 in front of y, negative 1 in front of z, 11 on the other side of the equal sign. Okay, and then for our second equation, there is a 1 in front of x, 2 in front of y, negative 1 in front of z, 3 on the other side. Last equation, there's a 2 in front of x, 4 in front of y, negative 2 in front of z, 10 on the other side of the equal sign. Okay. All right, so we're going to do our Gauss-Jordan elimination on this. So we are going to start in the first column, and we are going to want to secure a 1 on the principal diagonal. Okay, principal diagonal elements for this matrix are 3, 2, and negative 2. So we need to change our 3 to a 1. Okay, the easiest way to do that is to switch rows. Okay, you see a 1 right here. So if you just switch rows 1 and 2, or rows 1 and 2, you will get a 1 in this position. Okay, so again, I'm going to go ahead and write down my second matrix. Okay, I want you to notate, how you go from one matrix to the next. So let's go ahead and write down our shorthand notation. So to go from this first matrix to the second matrix, we're going to do row 1 and row 2 switched. So that's our shorthand notation. Row 3 is not involved in this process, so it will stay the same. Okay, and then row 2 will become row 1. And then the current row 1 will become the new row 2. All right, and so now we've got a 1 on the principal diagonal there. Okay, so we will carry on, okay, in column 1. Okay, so now that we've got the 1 on the principal diagonal, we've got to zero out the rest of the column. So we're going to change the 3 to a 0. Okay, so to get your zeros, you're going to do your third row operation. We are going to make a change to row 2. Okay, so in order to do this, we need to add to row 2, okay, a multiple of another row. Okay, so again, which row do you multiply by? Well, look at your column. You're in the first column. Find your 1 on your main diagonal. Okay, and then that 1 is in the first row. So that's what's going to get multiplied by something. That's why you always take care of the 1 first. Okay, well, what do you multiply by? You're trying to cancel a positive 3. So to do that, a negative 3 would cancel it. Okay, so our row operation is going to be negative 3 times row 1, okay, plus row 2 becomes the new row 2. Okay, if you multiply the first row by negative 3, that will put a negative 3 in this position. And then when you add it back to positive 3, you will get the 0. Okay, all right, so in my third matrix, okay, we are changing row 2. So I'm going to leave row 1 alone. I'm going to leave row 3 alone. And now I'm going to go do my workout to the side. Okay, I'm going to run negative 3 through the first row. So 1, 2, negative 1, 3. Okay, multiply every number by negative 3. We will get negative 3, negative 6, positive 3, negative 9. Okay, add this back to the second row up here. Okay, so we're going to add it back to 3, 7, 1, or sorry, negative 1, positive 11. Okay, we're adding here. Okay, so negative 3 plus 3 is 0. Negative 6 plus 7 is 1. 3 plus negative 1 is 2. Negative 9 plus 11 is positive 2. Okay, so that is your new second row. Okay, all right, still working in the first column. Okay, we've got to zero out this 2. Okay, so we are going to again do our third row operation. Okay, this time we are changing row 3. Okay, so we need to add to row 3 a multiple of another row. Okay, again, rely on that 1 on the main diagonal. Okay, in the first column, your 1 is located in the first row. So you're going to multiply the first row by something. What are you going to multiply by? Well, whatever cancels positive 2, the thing you're trying to get rid of. Okay, what cancels positive 2? Negative 2. Okay, so this is going to be our next row operation. Okay, you're going to do negative 2 times row 1. That will put a negative 2 in this position. Add it back to the third row, so add it back to positive 2. You will get the 0. Okay, so your fourth matrix, okay, you are changing row 3. So in this matrix, we are going to leave the first row and the second row alone. So I'm just going to rewrite them. Okay, and now I'm going to go do the work for the new third row. Okay, I'm going to multiply everything in row 1 by negative 2. So we're going to get negative 2, negative 4. Negative 2 times negative 2 is positive 2. Negative 2 times 6 is negative 6. Or sorry, negative 2 times 3 is negative 6. Okay, we are going to add that back to the third row. Here's the third row. Okay, so 2, 4, negative 2, 10. Okay, and we're adding. Okay, negative 2 plus 2 is 0. Negative 4 plus 4 is 0. 2 minus 2 is 0. Negative 6 plus 10 is positive 4. Okay, that's your new third row. All right, so we are done with the first column. Okay, you have a 1 on the principal diagonal. You've zeroed out below it. Okay, all right, so you are supposed to move on to column 2. Okay, you would start always by securing the 1 on the principal diagonal. Okay, so if you look at your principal diagonal, okay, here it is. Okay, the elements are 1, 1, and 0. For the second column, we would need to have a 1 in this position, and that's great, okay, because we already do. Okay, so now you want to zero out above and below it. Okay, so good news is below it, it's already a 0. So your next step would be to make this a 0. Okay, now we can go through the process here like we've been doing where you use your third row operation to get the 0. But maybe you've stared at this new matrix long enough and you realize something interesting. Okay, the bottom row, okay, the bottom row is 0, 0, 0. Okay, we saw something like this when we did the smaller system when we had 2 equations and 2 variables. Okay, and you have 0, 0, 0, and then the equal sign, and then something non-zero on the other side. Okay, so if you notice that, you actually don't have to keep doing the problem. Okay, if you didn't see this and you carried on and you did the row operation to get the 0 here, you would catch this in the next step. Okay, but always try to be cognizant of the matrix you're dealing with. Okay, because it can save you some steps. Okay, as soon as you see this bottom row 0, 0, 0, 4, okay, we know from previous experience with these smaller systems, when it comes time to put the 1 right here, there's going to be no way to do it. Okay, so let's go ahead and translate this last row. Okay, again, the first column are numbers in front of X. The second column are numbers in front of Y. The third column are numbers in front of Z. The third line is telling you 0 times X plus 0 times Y plus 0 times Z is equal to 4. That is what this last row is telling you. Okay, if you simplify that, okay, 0 times anything is 0. Okay, so we're going to get 0 equals 4. That is a false statement. Okay, so remember, every time you are solving a system of linear equations, there are 3 options. Either you're going to get exactly one solution, okay? Meaning you get the specific X, Y, and Z that works. That if you plug into the original equations, you get 3 true statements, okay? That's not what's happening here, okay? Because if there were a specific X, Y, and Z, we would have, ended up with the identity matrix on the left side of the vertical bar, and we would have gotten our X, Y, and Z, okay? When you can't get to the identity matrix, okay, that means you have one of 2 options. It's either no solution or it's infinitely many solutions, okay? How do you tell the difference, okay? Well, if it's something that makes sense, it's infinitely many, okay? If it's something that does not make sense, it is no solution, okay? So in our case, we get the statement 0 equals 4. That doesn't make any sense. It is never true, okay? So the answer to this problem is no solution, okay? And again, you did not have to keep going. As soon as you see 0, 0, 0, you know that's saying 0 equals 4. Nonsensical. No solution. Okay, done. Okay, so there is no assignment of X, Y, and Z such that if you plug those assignments into all 3 equations, you get a true statement in each single one. Okay, it doesn't work. Okay, so this is our first instance of no solution.